So I think we can start. If others will be joining, they would be joining. So we'll kickstart now, and that should be fine. Fine, sir.
Yes, Devansh, I am ready. We can start. Cool.
Okay. So first of all, thank you guys for joining. Thursday, 6 p.m. near there. Thank you for that. So without waiting further, I would like to introduce our guest or the man of the event, uh, Mr. Karthiganesh Durai. So he is CEO and founder of Quantum G Research Labs Private Limited, and he's also like a professor of practice in NMIT Bangalore. So we have been in touch for like last 1 2 weeks and discussing about how quantum ML could be the new thing or how it's affecting the industry and stuff like that. So it's my pleasure to invite him to the community workshop. Welcome, sir. Over to you.
Thanks, Devansh. This is amazing. Thanks for inviting me to share among people who joined on a evening time in India and morning or afternoon wherever you are. Nice meeting you. And let us start the journey of for the next 2.5 hours. We are going to um, discuss about quantum computing and quantum machine learning in general. Okay. Devansh, can I share my screen now?
Yeah, sir, sure.
Yeah, please. It's telling I'm not allowed to share my screen. While the screen sharing is activated, I will explain you the agenda for today. Predominantly, we are going to work on or we are going to discuss quantum machine learning. Um, but it is better to start with a small introduction. So what I'm planning to have for the next 15 minutes, very short, 15 to 15 minutes, I will give an introduction to quantum computing. Then 5 to 10 minutes Q&A on introduction to quantum computer. Then we will start quantum machine learning. The theory part or concept part, mathematical part, that will go for 45 minutes to 1 hour. Then remaining 45 minutes or 30 minutes to 45 minutes, I will demonstrate three models, quantum machine learning models: support vector machine, quantum neural network, and quantum convolutional neural network. Then overall we can discuss what are the other models and then what are the potential of using those things in the real use cases. And then we are going to discuss the suitability of quantum computing for industry production purpose, all those things. Feel free to ask a lot of questions because we are all in the learning phase. Hope you are seeing my screen. um, I think
It's
slide
not
should
visible, sir. You can
slide.
share now.
uh,
Yeah, sir.
Now, okay, right.
Yeah, yeah, it's visible, sir.
So if I slide show, what will happen? Still, you are seeing my screen. Still, you are seeing the slide, right?
Uh, yeah, sir. It's loading for now.
Yeah, yeah, yeah. For me also, it's loading. Yeah, right.
Yeah. Okay.
It's taking some time. Yeah, right. Um, a short introduction to quantum computing. Let me start with the image. So there is a latency when I click next tab. I don't know where it is moving. Ah, but it is moving fast. Okay, first identify this. There are 29 Okay, how many of there in the session? There are 38. Out of 38, I believe 30 members might have identified what is this one. Yeah, this is called ENIAC, an electronic numerical integrator and calculator. Oh, is this? Why it is taking a lot of time? Hmm, this is strange. Okay, right. So electronic numerical integrator and calculator. And those who don't know about this one, it was built in 1940 and it consumed 150 kilowatt. Right? It was in Philadelphia, and then the size is like you can see it is a mini bus size. Um, but in 2024, if you see, we are all handling this mobile phone, which is 450 times faster, and the size is 4,200 times smaller, and there are, and then that was in hertz, kilohertz. This is in gigahertz, so the speed is much. So over 50 years or 50 to 60 years of technological development, we are able to reduce that bigger ENIAC into a smaller phone. And what will happen in another 50 years? If you think through it, if you think about this one, what will happen in another 20 years, or what will happen in another 50 years? Obviously, we will have more smaller devices, right? More smaller computing devices, which consume less energy, more powerful. All those things will happen. So obviously, we will come to know what are those technologies, or which technology is powering those new computing engines. There are many: quantum computing, biological computing, optical computing, RNA computing, DNA computing. There are many computings coming into the technology world. We prefer, or personally, I like quantum computing, so I'm started focusing on quantum computing. So quantum computing is one way to build more powerful computers. Now you may have a question. Most of us know that there are working quantum computers, but still, I want to show that to make or to feel you more confident that yes, we are learning or pursuing something which is really working. There are working quantum computers available in the industry. To show that, I listed out working quantum computers. For example, IBM has 100 and sorry 1125 qubit superconducting quantum computer. Google has Sycamore. Then IonQ has built a quantum computer called Harmony. Honeywell is building another trapped ion system. Microsoft is exploring trying to build a trapped ion system. Then Xanadu Borealis is one quantum computer built on photonic quantum computing. Then QRA, Lucy, Atom Computing, they are all building quantum computers based on neutral atom technology. And in this one, the Atom Computing recently released 1180 qubit neutral atom quantum computers. Apart from this gate-based quantum computers, there is another set of computing devices called quantum annealer. With D-Wave, a Canadian organization, they are building a quantum annealer. They are also promising application of quantum computer for optimization problems. So these are all list of working quantum computers. So you can be very confident that yes, I am learning something which is there, which is physically built, and then people are started using that one. So I believe this will give you the confidence. Now you may wonder why quantum computers are so small or powerful. What is special about those things? I would like to recall the the smallest part of any classical computer, digital computer, is a transistor, right? A transistor, NPN transistor or PNP transistor, which is fabricated on an integrated circuit, IC chips, that uses a concept something similar to this analogy. As imagine that there is a football ground, thousands of football, 3,000 to 10,000 footballs in one goal post represent 0, and another goal post represent 1, right? Literally, transistors are moving from one junction to another junction in a sorry, electrons are moving from one junction to another junction in a transistor. That is what really happening. So 10,000 footballs are moving from one goal post to other goal post. That was classical digital computer transistor built upon. Whereas in quantum computer, they use only single electron. That's why it's called single electron transistor, SET. A single electron transistor Imagine that if a single electron transistor is put in the center of the football ground, football field, which side the goalpost? So we can there is a energy inside an electron which is called spin energy. That spin is a kind of momentum. It is called, technically it's called IAM, intrinsic angular momentum. That angular momentum may be in the upward direction or downward direction or any other direction. So the scientists and mathematicians decided the upward spin energy can be considered as zero. Since it is a movement, it is not just one number, it is an ket. So they put it as a zero ket, a vertical line, zero, and then greater than symbol, or downward movement, one ket. But since it is in momentum, it can be in other direction also, which calls as a superposition, psi ket, which means certain percentage of zero, certain percentage of one. That is what a quantum system capability. Because of the single electron is used to represent one transistor, one information, which we call it a qubit, quantum bit. Quantum computers are powerful because in classical few thousands electrons are doing some task. In quantum, only one electron is able to do not only that task, more than that, because of the superposition. So this analogy helps you to understand the reason for power of quantum computers. This is very layman term analogy. So if you exactly trying to connect with the scientific fact, there may be a here and there may be a gap, but it's a good start for non-technical people to start understanding qubits. So with this kind of capability, qubits, we are able to build quantum computers. So I would like to give a kind of semi-technical definition for quantum computers. A quantum computer is built on quantum mechanics. If you want to compare the classical systems are built on semiconductor physics or electronics. They are also called Newtonian mechanics. Then quantum computer operations are based on linear algebra of complex numbers operating in Hilbert space. So remember this one, linear algebra, complex number, Hilbert space. This is the mathematical model for quantum computers. Whereas in system, it is Boolean algebra, binary numbers, metric space. So Boolean algebra can be converted, the Boolean algebra operation and are not those gate operation or binary number 0 and 1. That is powering the classical system. Now you understand a binary number compared to complex number. That itself will help you to understand why quantum computers are powerful. And building blocks of quantum computers is a qubit. But the quantum computers are operating at a subatomic scale. They need sophisticated engineering capability. So when I mean subatomic scale, I'm referring fundamental particles or atomic particle like electron, neutron, proton, but I'm still going further. Quarks, leptons, bosons, those kind of fundamental particles. Now you understood. So it is subatomic scale, which we cannot visualize with our normal eyes. We need sophisticated magnetic or nuclear based scanning or tunneling systems or measurement or control systems to manipulate quantum computers. That's why quantum computers are costly. As of now, in the year as of 2024, they cost 15 million to 40 million dollar to build a quantum computer. So it is really costly affair. That's why not everyone or all organizations are not able to build quantum computers. This will give you a good idea. With this introduction, let us move on to the quantum behavior. There are three behaviors: superposition, entanglement, interference. And these concepts beaten to death, so I'm not spending time there. And the qubit also, spin or photon, these are all used as a qubit. So the psychet, which is mentioned here, that will help you to understand the value is in between 0 and 1. Okay. Then we can build qubits using various technologies, but only the top technology: superconducting, trapped ion, photonic, neutron atom. These four technologies are matured now. We are expecting other technologies will also find some technological advancements, and then we are able to build more powerful but smaller size quantum computer. When I mention smaller size, you may wonder what is the size. So if you assume that this is the architecture of digital computer, which having motherboard, graphics card, RAM, HDD, then processor. Inside the processor, we have instruction register, program counter, decoder, all those things. Quantum computer architecture is bulky. It will be chandelier. You can read chandelier, right? It will hanging chandelier structure, and it has qubit signal amplifier, microwave lines, coaxial lines, cryogenic isolators, mixing chamber, uh, cryo pump shield, all those things. For your information, this image is taken from IBM quantum model. In general, this is the architecture of quantum computer. Here you can see the refrigeration unit, what I put here. That refrigeration unit, this unit is a cryogenic engine based refrigeration. The reason is that the processor, here is the processor, it need to operate at minus 273 degrees Celsius, which is cooler than outer space. And a cryogenic refrigerator. So because of all those things, in 2024, quantum computers are bulky, very big, and that's why their cost goes between 15 million to 40 million. Hope that will help you to understand why quantum computers are costly. Now, if you want to understand how the timeline, it started with double slit experiment, then black body radiation, then quantum tunneling, quantum entanglement. All those things are happening on the quantum mechanics. But quantum computing started 1981 by actually 1960. The mathematical concepts were introduced: conjugate coding, reversible gates, superposition, and all. But quantum information theory was proposed by 1981 by Richard Feynman and Charles Galois. So they proposed building a quantum computer using quantum behavior like superposition, entanglement, and interferences. And after that, 1994 Shor's algorithm, 1996 Grover algorithm, and then there are many other algorithms help the industry to take quantum computing as a viable technology and then start researching on those things. And in 2023, we are having 1125 qubit quantum computers. It is a short introduction or history of the quantum computers. But now you may want to know, actually, really, who are all working on the quantum computer? Is it really worth? Now you can see here, this is the quantum computing ecosystem in 2022 May, 2 years back. The latest one will have is having more images, more organization started working on quantum computing ecosystem. This is the international ecosystem, and if you see in India, this is a national effort. You can see here there is a government organization, all IIT, IISc, ICER, they are all into the research side. Then there are many organizations on the startup side, QIA, QNU Labs, Qkrishi, and these are all startups. And there are service providers. You can see here all the software service providers: TCS, HCL, Tech Mahindra, Infosys, Accenture, Capgemini, all are into the quantum computing based research. Then academia, all academia. See, in the government organization, it is DST, CDOT, DRDO, CDAC, all organizations, research organizations are into quantum computing. Hope this helps you to understand there is lot of efforts are going on in the um, quantum computing side, both internationally and nationally, at both levels, global level. With this introduction, national efforts is gaining momentum now, and after the national quantum mission, what Government of India asked for proposals from government, various organizations in India, which closed on 19th April. Yeah, 19th April was the last date. And for those who are here, I am the part of two proposals submitted to National Quantum Mission. Waiting for the approval. If it is confirmed, I can proudly say that I'm working on two quantum national quantum mission projects. That is one thing. Then comes startups. Government of India is planning to support all the startups and then educational institutions to build the human capital. And this is a cost. Here you can see worldwide it is $36 billion is invested on quantum technologies, and as all of you know, India is invested 6,000 crores. Here it is 8,000, 6,000 for quantum computing, 2,000 crores for artificial intelligence. So that is what the 1 billion allocated by India. And okay, I think this will give you a good idea. In another 2 minutes, I will close this introduction. There are the software frameworks. If you want to work on quantum computing, you can choose any one of these or all those things. For your information, I almost worked in all of these things, and some of the things what are not listed here also I'm working. And there are quantum cloud, IBM, Amazon bracket, Azure Quantum, then Google Cloud. Then our important part comes, where are we using quantum computing? There are many: AI and machine learning, computational chemistry, drug design development, cyber security, financial model, logistics, weather forecasting. Now you may ask, why not database management? Why not graphics? Yeah, it is not required because quantum computers are much powerful. They can solve an area called non-polynomial time problems, which are very difficult by classical system. Because if the classical system, if you want to break a cyber a cryptographic key, a classical system will take 4 years to 8 years, because that is a non-polynomial time problem. Whereas quantum computer can solve it by with a proper maybe 100,000 or 1 lakh qubit. Quantum computer can break a cryptographic key in 4 hours to 4 days. Within that period, it can break. So those kind of problems. Because of that one, quantum computers will not replace classical system. They will complement classical system. So it will be always CPU plus QPU, like CPU plus GPU, CPU plus TPU. There will be architecture CPU plus QPU, quantum processing unit. It will be always like this only. QPUs will not replace CPUs. So who are pursuing classical computing, they are also will continue getting jobs. Don't feel that, oh my god, quantum computer will replace. It's not the case. Quantum computing will build its own computing capabilities. So there will be a set of people expected to work on quantum computing. Classical will continue grow. So these are the areas where we are using quantum computing. And the future of quantum computing is really bright. We are in the first generation of quantum computing. You can see here 2018 to 2028. By the way, this is by BCG, Boston Consultancy Group. And second generation is from 2028 to 2039. And the third generation 2031 to 2042. So who are all entering the quantum computing now in the year 2024? And we are entering the first generation. We will become early entrant. Those people can be considered somewhat equivalent to those who entered computer industry in 1980s. That kind of advantage we will get into quantum computing if we enter now, 2024. Okay, hope this helps you understand. And quantum computing, as I pointed out, all the applications will be covered by quantum computing. If you want to learn quantum computing, this is the path. Identify the domain: finance, cryptography, QML, any domain or application, whatever I have told now. From there, understand the physics, then learn mathematics, then learn computer programming. Don't start with the computer programming. Learn domain, physics, mathematics, and computer programming. But when you work, you will start from computer programming. Got the point, right? So the sequence will be like this, in this order. And what you have to learn initially, you have to learn most of the quantum computing algorithms, how they are working, what is the mathematical model behind it, how they are providing the parallel processing capability, and how they can be used to solve non-polynomial time problem. These are the things you have to learn to pursue quantum computing. And this is my favorite slide. This is from the movie called Transcendence by Johnny Depp and John Morgan. This is an amazing movie. If you have time, please watch this movie. You can understand how artificial intelligence is helping quantum computing. After that, how quantum computing is helping artificial intelligence. It is like, help me first, I will help you later. That kind of structure. With this, I will end my first session. Open for Q&A. Sorry, I took more than um, 4 or oh my god, more than 10 minutes. Sorry about it, but this is necessary. Now I'm open for question answer for another 3 to 5 minutes. Audience, anyone have any question? This learning path is very interesting. I just go through. If you have any question, just stop me. I will explain that slide. You think quantum mechanics is very, you understand? Actually, you don't understand. Um, it is not that much difficult, but it needs repeated efforts, not just um, one day efforts not sufficient. You have to repeatedly listen to those technical terms. Got it? Okay. Again, I will go back in another one more minute.
So I have a doubt.
Yeah, please
So
go
you
ahead.
had mentioned that the learning path starts from physics, maths, and then goes to computer science, right? But most of us here are from the computer science background itself. So, and mathematics, the most of mathematics that we know is from high school or college. Now, with this background, how do we shift to quantum?
Yeah, that's why I put, see, because since most of the computer programmers, it is easy for them to Google IBM Qiskit and then get a source code and run it and then assume that they know quantum computing. Do you understand what I'm pointing out? Because since we are programmers, I also software engineer. I am from computer background. I also thinking that like that only. Yes, some program, a quantum computer program, if you are able to run on this one, I know quantum computing. That's what I thought when I started learning this quantum computing. Later, I realized that that is only tip of the iceberg. The programming part is tip of the iceberg, but the real problems lies in the mathematical model. To understand the mathematical model, you have to understand how the physical system is working. So at the end of the day, all those things used for some application. Why? So if you start from why question, that start with the domain. Why are you doing this? I am doing this for quantum machine learning. I am doing this for quantum finance. I am doing this for quantum cryptography. Or I am doing this for healthcare, quantum computing for healthcare, or quantum computational chemistry. Like that, you have to identify one domain. That is where you understand why part. Why are you doing all those things? And a computer developer or programmer cannot understand all the concepts because that domain problem itself very deeper. If you take quantum machine learning, the person must be a strong machine learning, classical machine learning person. Then only he will know the non-polynomial time problems. He should have some experience where he is facing his model is taking long time to train or long time to classify or predict. After that only you can understand how I can convert or how I can improve this problem into quantum computing. That's why I put start with the domain. Understand what is your domain. You are a finance person, or you are a quantum machine learning person, or you are a physics person, or you are a healthcare person. Like that, you have to identify one domain. Then for the domain, if you are trying to solve the system, how the physical system is working, how this superposition, how this entanglement, how this interference are behaving, that you have to clear. After that, those operations how mathematically represented, then how that mathematical models implemented in programming. So this one cycle, after that you stay in programming. You got my point? Don't neglect
Yes, sir.
physics mathematics domain, don't stay in programming only. That one will not help, because when a quantum computing problem is given to you, it is not the syntax of Python or syntax of Qiskit, syntax of Blockhead. That is not a big deal. That you can easily understand how that mathematical operation behind that syntax, that helps you to fix the issue or improve your problem. You got the point?
Yes, so extending my doubt, extending my question, can I ask one more thing?
Yeah.
So, in the people that you recruit as a quantum
Hmm.
scientist or a research scientist, what are the few projects that they would have worked on, or what are the few projects that we can have as a startup for? For example, if anyone wants to go for web developing, generally someone will start with a to-do app or an expense tracker app, right? I do understand the scale of quantum cannot be subscribed to that, but is there some particular problem statement where we can, that's quite famous, where we can start from, and then eventually get a gist of it and get into it?
See, whatever domain, whatever problem you are working, you must have fundamental knowledge of all these algorithms. That is must. You must know all this algorithm at the first. After that, you should have your domain. For example, if you are an optimization person, you should have worked in QA or Cubo. If you are an engineering person, you should have worked on linear solver, VQLS, HHL, those algorithms. If you are a quantum machine learning person, you should have worked on quantum support vector machine, quantum neural network, QCNN, quantum convolutional neural network, quantum transfer learning. These are all for quantum machine learning. If you are from the specific industry like healthcare, at least you should have worked in molecule energy optimization using VQE. These are the things for specific area. Does it answer your question?
Yes, sir.
Great. Very good questions, an interesting question, and I believe that it is useful for all. Any other questions?
Yeah, Mr. Karthi, can you hear me?
Yeah. Yes, I'm hearing you.
Sir, I have a doubt. So you said quantum computing can be used for solving non-polynomial problems, right? And you also touched
Correct.
upon the optimization side. So
Correct.
I'm just curious to know whether this quantum computing algorithms can help convert those non-polynomial problems into polynomial problems. For
Actually,
example, if I'm connected to optimization, so we have all this vehicle routing and traveling salesman kind of problems, which typically fall into this NP hard category. So if we
correct.
try to solve using normal computing power, it will take a lot of time to solve. So they are basically polynomially hard. So my question is, will applying this quantum computing can convert that non-polynomially hard problems into a polynomially solvable one?
See, that is a holy grail of all mathematicians, physicists are looking for, right? Is there a holy grail where I can make P NP equal to P? Correct. When that happens, most of the computing problem in the world will be solved, right? When NP equal to P. And what quantum computing is promising, that not for all NP can be converted into P, but we can approach the NP in a different way, such that some of the models, why they are NP hard, because the mathematical model are sequential in nature. So because of the sequential in nature, it is going to the exponential or any non-polynomial approach. Whereas quantum computing is telling that this sequential approach, wherever possible, can be parallelized. So those problems like optimization, because we have to find out the global minima, right? That is where optimization problem. A quantum system can naturally go to the global minima without much efforts. That kind of setup, those kind of mathematical models, only converted into P problems, not all NP hard problems. There is a limitation to quantum also. only we identified 3 to 4 areas which are which can be optimized or which can be parallelized using 3 properties: yeah, amplitude, phase, or both of these 2 things. So if you are able to represent your information either into a phase or amplitude or both, those problems can be converted into polynomial time problems. Does it answer your question, Dr. Ram
Yes,
Subramanian?
sir. Yes, sir. Understood, sir. Thank you. Thank you so
Great,
much.
thank you. Any other question? Okay, I think no more questions. Let us move on to quantum machine learning. Now I would like to give an introduction about me, because that will help you understand why I am explaining quantum machine learning. So I started my career as a software engineer in late 90s. So I started working on COBOL programming, then moved to Fox Pro, then Oracle, then SharePoint, then Visual Basic, then Python. Then later, because when I moved to SharePoint and all, I was closely working with management. So the management people asked me to build some analysis. That time, data science is emerging. They asked me to work on certain analytical models. That is where I introduced to data analytics. So I started working on R language 2007 and 8 onwards. Then I realized the potential of data science. So I started learning R language, Python language in parallel. Then later, over a period of time, when Python matured, when I started, Python was not matured enough to handle data analytics or data science. Later, it is matured. I also learned Python-based data science. So I became a data scientist. So 2013 to 2023, I was a data scientist working in Dell Bangalore office as a data scientist. Then I resigned my data science job, then enter into quantum computing. This is my software journey. Now I will start my quantum journey. I started observing about quantum computing since 2004. Then I did my master project on quantum computing algorithm in 2010. Then still I'm continuing learning quantum computing or self-learning, and wherever I'm getting opportunity, I will talk to professors, try to understand the mathematical model, physics model, chemistry, underlying chemistry, all those things I started learning. Programming is my area, so I never had need help there. But I realized that without understanding this mathematics and physics, I cannot understand quantum computing or quantum programming effectively. So I 2010 onwards, I started studying mathematics, physics more deeper. Then in 2019, I one of the founder. I formed Quantum Computing India. That is where I come to know about the Boson QSI, and I closely worked with the CEO of Boson QSI. Then we realized that I have the capacity to work on their quantum problems. So I started working on quantum computing. This is my journey on the quantum. So there are 2 parallel journeys with me. One is classical, other one is quantum. So quantum side, I'm able to reach or achieve my goal of becoming a quantum computing professional in the year 2019, but I became a full-fledged quantum computing professional last year. And now I started my own organization for quantum computing research. So this is short introduction about me, because that will help you why I'm explaining quantum machine learning. Now I'm moving on to quantum machine learning. Let me share another screen. Hope you are seeing the quantum machine learning screen. Okay, I think I need few more minutes. I would like to give you. Okay, right, yeah, it's good, no problem. Right. So in the quantum machine learning, why quantum machine learning um, suitable for quantum computing, or why quantum computers are necessary for quantum machine learning? That's what we are going to discuss. It integrates quantum algorithm into machine learning, because most of the machine learning problems, if you check the quantum computing basics, it is a information processing. Then the qubits are both states. Then qubits enable parallel processing. So this superposition and entanglement, these things are helping machine learning models or machine learning problems to be executed in parallel, such that they will achieve the performance required for training, classification, prediction, or feature map, all those. But we should know classical machine learning also, right? When we discuss the quantum machine learning, I cannot assume that all of you are very good about quantum classical machine learning. So I want to touch upon these concepts. There are algorithms for deep learning, and then there are foundational methods for um, then supervised learning, where we have the labeled data set. And normally supervised learning may be a regression or classification. If it is a numerical data, it is a regression, and then categorical data, it will be classification. And there is one more model called unsupervised learning, where we don't have labeled data set, and there we will use k-mean clustering and those techniques and principal component analysis. Then the other area also called semi-supervised learning, reinforcement learning. These are all various classical machine learning models. Okay. So this will, it is a kind of refreshing or refreshing your knowledge on the classical machine learning. With this one, I would like to focus on applications of classical machine learning. I think most of us know that classical machine learning, artificial intelligence on ChatGPT, Midjourney, those kind of generative AI, that is the current trend. But classical machine learning can be used for all these things also, like healthcare, predictive, personalized treatment, then medical imaging analysis, drug discovery, in the finance, fraud detection, risk assessment, trading, then in the e-commerce, product recommendation, customer churn prediction, price optimization. In marketing, we have sentiment analysis and other things. These are all applications of classical, which means applications of quantum machine learning also, right? Some of the things I will discuss when we discuss the program. I will explain. So this Venn diagram explains you clearly where quantum machine learning intersect. So it is a knowledge of a skill on machine learning, quantum computing, and optimization techniques. So that is what QML. So if you are telling that you are a QML expert, you know all these three things: machine learning, automation techniques, and then quantum computing, right? And what are the benefits of QML? Why not say, when classical machine learning is there, why should we go for quantum machine learning? First one is speed up. The speed up, exponential speed up provided by quantum computers, or something what classical system looking for. Of course, classical system also making lot of advancements in the form of HPC, GPUs. These are all providing the necessary speed for classical machine learning. But still, some of the problems are still slow in the classical machine learning model. Then the approach, the mathematical model itself, it will open up a different possibilities for building machine learning models. Because of that, we are able to build new algorithms also. For example, um, there is a learning called transfer learning. In the classical transfer learning, it is not achievable because classical transfer learning always um, give you the, what is called, it won't give you the necessary accuracy. If you want to get that accuracy, the model processing is very uh, how to say, it will take more time because of the NP hardness, whereas quantum transfer learning can do it naturally. Like that, there are new possibilities are coming in the machine learning model because of the quantum computing capabilities. So there are those are classified under 5 parameters: speed, accuracy, security, scalability, novel applications. Here, the accuracy part is something people cannot understand or appreciate closely. For that, I would like to spend some time. So there is a concept called approximation. All classical systems are approximated system, meaning that the input is approximated into binary numbers. All of you agree with me? The, the digital computers are not processing the actual number with the actual accuracy. We are all approximating a real number into binary number. Correct? Am I right? That's what happening in the classical systems. Whereas quantum systems are able to process complex numbers, which means they are able to process the information without approximation. That is the important concept you have to understand. Because of no approximation, quantum systems are more accurate. Of course, the current technology is able to offer only the NISCARA, I mean noisy intermediate systems, right? We are having noisy intermediate scale quantum systems only. Because of that, the accuracy is not the same way what industry is predicting, or industry is proposing that quantum computers are more accurate. But when we have a fault tolerant quantum computers, that accuracy cannot be compared with the classical system. The real number can be fed into as it is. Imagine that you are building a precision agricultural system. We need to feed the moisture or nitrogen content or any other parameter as it is to the model to predict or to classify. A quantum sensor can feed the number accurately to the quantum computer. There is no any approximation. Then the classification or regression performed by a quantum computer will be the highest accuracy level, because it is processing the natural number without the number in the nature without approximation. That is the main reason why I spend some time. See, when many people are asking about what is the advantage of quantum computer, we used to tell speed up. It is not speed up. The accuracy is the main reason, because we don't approximate the number. Without approximation, we are feeding. That's the reason why quantum computers are offering more accurate result. Keep this as one of the parameter. Don't always think that quantum computers are offering speed. Speed is one of the capabilities or one of the advantage. The accuracy without approximation, that is one of the real thing which classical system cannot achieve. Because when we say about speed, there are HPC system, there are QPUs, there are GPUs. They can give the accuracy, they can give the speed, but still they can't give the accuracy because they are all operating on the approximated data. So keep that in mind. And then security. Security, the quantum systems are fragile. When you are communicating the quantum data through a quantum channel, no one can hack it. The moment anyone try to touch it, the information will collapse. That kind of security is not provided by classical system, because classical system is sending 10,000 electrons, right? One of the few electrons, if we take it out, the Alice and Bob is not going to know. Whereas when Alice send only one photon or one electron, and Charlie is trying to hack it, everyone will come to know, because that is only one fragile information is being transmitted. Then comes scalability. Scalability is what industry is working now. When more qubits comes, it will be scalable. Now you will wonder how it is scalable. And for this, I have to call the formula. N qubits will give 2 power n, right? If there are n bits, we can represent 2 power n numbers, meaning that if you have 4 bits, you can encode or you can represent 2 power n, meaning that 16 numbers, right? 16 numbers in the classical world. Quantum also same, but here the one difference is at the same time all the 16 value will be there. That is the property which is offering scalability. See, at the same time means I have to go back to the introduction. Remember the qubit, and they are in the superposition. When the system is in superposition, see, imagine that there are 3 qubits. So there are 8 possibilities. Your 3 qubits will be in all combination at the same time, but with a certain probabilities. Some probabilities for 00, some probability for 001, some probability for 010, some probabilities for 011. We call it as alpha 1 probability, alpha 2 probability. If you put mathematics number like that, you will have alpha 8 probabilities. Sum of the all alpha equal to 1. So if you have 4 qubits, there will be 16 alpha. If you have 5 qubits, you have 32. All at the same time. Same time means in the same time. Without in classical system, it will be for each clock cycle there will be different values. At one clock cycle, it will have only one value. But in quantum, there is no clock cycle concept. Before measurement, the quantum system will be in all values. Only thing, the probability will change. The highest probability is our result. That is how quantum algorithms are built. That is the reason why you should know probability also. When if you are learning quantum computing, you have to learn probability also. So these are all the benefits for any quantum. It's not only for quantum machine learning. This is applicable for quantum optimization, quantum machine learning, or quantum simulation. Everywhere these advantages are applicable, benefits. Then comes approaches. So for building a quantum machine learning, we have 4 approaches: classical data, classical algorithm, classical data, quantum algorithm, quantum data, classical algorithm, quantum data, quantum algorithm. See, the quantum data, quantum algorithm is the dream. That is where the industry is working. If you have the quantum data and then quantum algorithm, all the advantage, whatever I'm telling now, they will be realized. Till that time, we are compromising one or other things and then trying to build the systems. Hope this helps, right? So for another 10 minutes, we will see theory. Then we will enter into programming. Okay. I will walk through, maybe now it is 7, right? Around 7:20, or 7:20 or 7:30, I will start the program. Now I will want to go back and then answer your questions. If you have any question, feel free to, because I keep on talking, you will you will feel like, oh my God, this person is non-stop radio. It is broadcasting. I don't want to broadcast, I want to interact. Please, any question in these slides? I'll wait for 1 more minute. Okay, let me ask one question. Can you answer this question, yes or no? There are 34 members. Let me see how many are answering. Only 2 members answered that they understood why it is accurate. Why don't others please type Y? Y for yes, N for no. Only 1 letter. Rakesh, yes. Okay, good, good. So far 3 members. Sandan Lashmi, yes. Mahendran, yes, yes. Rachel, yes. Ashwin, great. Anyone don't understand? Amazing. Sangeeta put the exact word. They process without approximation. Remember that word. Quantum computers process without approximation. That is the exact technical term to convince others. Amazing. Cool. Amazing. You are all listening very carefully. That's very interesting. Cool. Let us continue the approaches, 4 approaches. Let me stop this one. Oops. Okay, right. You are seeing my screen clearly, right? What happened?
Your screen is visible, nice, no worries.
Okay, okay. But I am not able to move to the next slide.
It's in the introduction slide, the second slide actually.
Oh, yes, yes, yes. Okay, okay. Now I got it.
Yeah.
So in classical machine learning, then application, then intersection Venn diagram, then benefits of QML, then 4 approaches. All are good, right? Now I'm going to explain the 4 approaches more detail. Both data and computation remains classical, then combined quantum and hybrid, where combines classical data with quantum computation. Then classical algorithms also there, and this is where we are now. Classical, then classical quantum and classical, then classical quantum data quantum. So qubits encode the process information, all those things. Here, one thing what you have to understand: classical data. When I say classical data and quantum data, you understood that accuracy we are getting because of no approximation, which means the data, it should be a real number data, because we deal with real number, so we understand real number. See, if I tell that, see, for example, I'm measuring you are feeling fever, so I'm measuring the temperature. I'm telling, oh, you have 36 point or 37.2 degrees centigrade temperature. You can understand because it's a real number. If I tell that 36.7 plus 0 I temperature, will you understand this number? You can't understand because this is complex number, because we never counted or we never used the complex number, but we are comfortable with the real numbers. But whereas quantum is representing all as a complex numbers. So if you are able to feed the information which occurred from the system naturally without any approximation as a complex number, the quantum algorithm can directly process. That's what I mean by quantum data, right? Quantum data should come from the source as it is. For that, we are using quantum sensing. There is a new technology called, not new technology, old technology, but a maturing technology called quantum sensor, quantum metrology, or quantum sensing. There are devices, or there are sensing devices which can get the values of fundamental properties. Those things are quantum data, because only those information can be processed by fundamental particles which are used inside the quantum computers. So that level, the whenever I'm mentioning the qubit encode process information, all those things, I am talking about the number or value in complex numbers which are used to represent the fundamental properties of fundamental particles. That level we are talking. Then comes, now with all this data preparation are set, now let us come to quantum computers. In the quantum computers, there is a circuit called parameterized quantum circuit. That is an important concept. It is a jump in the concept. The reason is that actually I planned off from here. I will stop. Usually I will stop and then demonstrate IBM quantum. Then I will move to that one. Shall I stop here, move to a demonstration of IBM quantum, then come back to the next slide, because that will be more meaningful. Let me start IBM quantum. Quantum.ibm.com. I'm not sharing that screen. Give me a second. I'm going to share the screen. Okay. Now, hope you are seeing, all of you seeing my IBM account, right? I'm logging into my IBM cloud. This is my username and password, and I'm going to enter TOTP. I will enter the code. I have a device with me, Microsoft Authenticator, where I have this IBM account added. So from there, I am entering the TOTP. Give me a few minutes because it is 3 seconds now. Okay, now 30 seconds. So this is where you can learn quantum programming. There are two ways to write the programs. One is IBM Quantum Composer, other one is IBM Quantum Lab. Unfortunately, IBM is going to close this Jupyter Lab on 15th May. So let me show IBM Quantum Composer. So IBM Quantum Composer is a good learning tool where you can design your circuit. This is circuit, quantum circuit. It is something like, if you are coming from digital electronics, you used to design the circuit, right? We using AND gate, OR gate, NOT gate, like that. Something like that. If you are coming from digital electronics, if anyone who are not from digital electronics, they may found it is very difficult. For them, how can I explain? You may see the AND gate, OR gate, this kind of circuits. See full adder. 1 minute, I am switching to another window. So these circuits, these are the circuits, right? These are all called digital electronic circuits. Something like that we can build using quantum gates. That is the quantum circuits. Those kind of circuits we can design, right? Here, I would like to stop everything. Okay, so this is the circuit. Imagine only these things. Later, other things I will show later. Here, what I can do, I can drag and drop the gates. So if I want to perform this gate, what is this gate doing? Don't worry now. Just understand this. These kind of things are possible with the quantum circuits, right? So I can perform these kind of operations and then perform these things. So that's it. That is what building a quantum circuit. This circuit will do something. What it is doing, this is randomly I placed, so it doesn't make any sense. But if you understand the mathematical model and the expected output, you know very well what you can do things. That is how you are building the circuit. So if you want to build the number of circuit, you can go here, manage register. You can build qubit, 4 qubit or 5. The number of qubit and the number of classical bits should be same. So, and if you want to perform a Bell state, what you will do, you will put a Hadamard gate, then a CX, control X. This is CX gate. If you want to understand, select this one. You can see the name clearly. Hadamard gate, not gate, C not gate, like this, you can understand clearly. If you don't understand what the gate, go to the gate, right click, click info. That will tell what is this T gate. The T gate is equivalent to R is at for the angle pi by 4. Like this, it will tell all those things. Got the point? So it is easy to learn this way through IBM Composer. After this is the graphics editor. You see this face disk that will give you the value of the qubit, and you can activate other panel state vector that will tell you the state vector of this qubit system, or else you can view the probabilities of the system. See, the probability will show you. Remember, I told you 4 qubits can be in all 16 values at the same time. This is what that same time. The probability of the state 00 is 50, 011 is 50, others are 0, which means the the system can be in these two values only. And then this one is amplitude of the Q of the 4-qubit system. Their amplitude will be high for the 00 bit, and then this bit will be high. Similarly, there is one more way to view, which is called Q sphere, that will show the 4 qubits where they are fall into. See, this is, I am using only 2 qubit. So if I put one more operation here and one more operation here, and then put one more Hadamard gate here, you will see the values are distributed. Now you can see 8 values. And if I put here, because it is superposition, when it is in superposition, you can see all values are in the same time. So this way you can play around. This is called quantum circuit. But you may feel that, oh my god, I am from programming, I don't understand, what are you doing? Is this programming? I don't feel that this is the programming, and I did not expect this one. Don't worry, this can be converted into a program by seeing the code editor. See here, now you can see the whole operation, whatever we have done, written as a Python program, which is I can copy this code and then put into my Visual Studio Code and then see. Don't worry, my screen is not shared there. I will share that option now. Hope you are seeing my Visual Studio Code, right? So here you can see it looks like familiar, right? If you are coming from computer science background, wow, this looks nice rather than that circuit. But ideally, the learning process is that you should learn from there only. You should comfortable seeing those circuits and understand what they are doing. That is the good starting point. For any reason, if you feel that this circuit is not suitable for me, I don't understand, it is not making sense to me, please spend some time trying to understand this circuit, because that will give you the right direction to learn the quantum programming. Okay, so this circuit can be converted into a Python program. Since it is in Python program, you know very well the class concept, the function concept, def, all those things are applicable for quantum machine learning also. If you are a strong Python programmer, you can create a class for quantum support vector machine, another class for quantum neural network. Like that, you can build multiple classes, then bring them into one program, then get a result. You understood, right? See, once you know the concept, these concepts, mathematical concepts, circuit, gate, how they are behaving, how they are phase, how their energy resulted in the phase disk info, all those things, you are enter into a new world. You will be able to understand what will happen if I put other gate, because this phase disk, this is key here, not the Python program. The circle, the blue color and then gray color circle, that is the key here. To see this one, you have to do the inspect mode. In the inspect mode, you can see here, each time the disk will change. See, let me put some more operation. That is the key here. What I recommend, play around initially. Don't hurry in the quantum computing career. That won't help. Minimum, you need to spend minimum 9 months of efforts. Then only you will be able to understand most of the concepts. So plan minimum 3 quarters. It is not 1 month or 2 month affair. You have to stay there minimum 9 months to understand. So spend 1 month fully on quantum circuit. Nothing wrong in it. So now you see, when I end the all Hadamard gate, you can see only 3 gates are in the superposition. This one is 0 probability, or 100 probability for state 1. When I put the CX gate, you see here, these two things are in the different level. Probability of 1 is 50, purity is reduced. Here, purity is not reduced. Like this, each step will show the different phase disk information. See, forget about the state vector probabilities Q sphere. First, try to understand this phase vector. This is essential. Also, one more thing is, there are many visualization for Blochsphere. Learn from that one also. These are all foundational concepts. Whatever I am telling now, they are all foundational concepts. After the foundations are strong, you can learn anything in future easily. But initially, it may look like, oh my God, it takes a lengthy process. Obviously, it is a lengthy process. If someone is telling that you can become a quantum computing professional in 1 month or 2 months, please, that don't believe them. That is not possible unless you are already having physics and mathematics and programming knowledge already. If you have all these 3 skills already, then you can become a quantum computing professional in 1 or 2 months. If you don't have those fundamentals, it will take minimum 9 months. That one, it is the starting point. Play around, understand. So this is the quantum circuit. For the corresponding quantum circuit, you can see a Qiskit Python program, right? Here, I would like to stop and answer your question for 2 to 3 minutes. Then we will move back to quantum machine learning. Any question in the IBM circuit composer?
Uh, Karthiganesh, will you please demonstrate the simple two-variable binary addition if possible, if time is permits?
Actually, there is a full ladder circuit in quantum circuit. It is there. But if I start explaining that one, it will deviate. It will take more time. We will miss time for quantum machine learning. I recommend you to please connect with Devansh or Nivu. They will connect you with me. There we can discuss offline. But there are circuits for full adder and gray code, then quantum Fourier transformation. These are all small algorithms. They are there. But normal arithmetic operations, we won't use quantum computer. But for the sake of learning purpose, there are small algorithms are there. Does it answer your question?
Yeah, thank you.
Thank you. One more question. We have time for one more question. Anyone? Yeah, Nishant, please go ahead. Do a mimic performing binary arithmetic in IBM. Oh, that's what. Okay, yes, yeah. Nishant, do you have some question, please? Okay, Rakesh, you have raised your
Yeah,
hand, please. Yeah,
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 yeah.
Rakesh.
See, I have a doubt regarding this diagram, just your this connection.
Uh-huh.
Uh, so you were talking about support vector machine, right? So,
Uh-huh.
assuming that I'm having 4 feature variables,
Mm-hmm.
and okay, I'm predicting something like a supervised learning.
Mm-hmm.
So in the right side, I get the probability, right? So I will
Mm.
go for maximum probability 1 and least for 0. Like that, it works, right?
It is, see, in these support vector machine, the way how it works, the probability of that particular class, meaning that I assuming that iris classification, I am
Okay.
classifying whether it is Setosa or versicolor or virginica, right?
Yeah,
So
yeah.
there will be 3 possibilities. So for a given input, the probability in the form of any one of these state will become high.
Yeah,
And
right.
yeah, your understanding is correct. One
Yeah,
more
yeah.
additional concept is that probability is not one single time task. It will be repeated 1,000 times.
Yes, yes.
That is the difference between classical system and quantum system. Because In classical, if we get one probability, that same probability will be repeated any time, meaning that 2 plus 2 always 4 in classical. But in quantum, 2 plus 2 sometimes will come 3.9, sometimes it will go 4.04, sometimes it will go 3.7, sometimes it will go like that, it will go. But most of the time, number 4 will come. So the highest probability comes for 4. So we are assuming 2 plus 4 equal to 4. That is how quantum computers is working.
That's why you're explaining there is no approximation, right?
Exactly. Yeah.
Yeah. So, and my simple doubt is that what is going to be my input? Suppose I have four continuous features. Where I'm going to give this, because these gates take 0 and 1 only, right? As the initial state. We have
Yeah.
4 qubits here, right?
That is the question on the hit of the bullseye. I will tell you. That is a great question. Let me go back to the quantum machine learning. I will share this one. You see this question. You see these four approaches: classical, classical, quantum. Here, for this
Yeah.
one, there is a concept called this encoding, quantum information encoding.
All
The,
right.
the classical information can be encoded as basis encoding or phase encoding or amplitude encoding. This is how you convert your 0 to 1 into a quantum information in the form of the basis point. If there are 3 qubits, the basis encoding will make one of the 3 qubit as the value. In phase encoding, we will put the angle. Your data will be converted into angle and then put into qubit. In amplitude encoding, your data will be converted into amplitude and set into the amplitude. These are the encoding system used to convert your binary data into the quantum data. That is the input we are giving. If we take iris example, when I give the four parameters, what is called length and
Petal
width
and
of the
sepal.
four,
Yeah.
petal and sepal, right? Petal
Yeah.
and petal, sepal and sepal width. There are 4 parameters, right? When I give the 4 parameters, these 4 numbers will be converted into a basis encoding or angle encoding. But mostly it is in the quantum machine learning, we will use phase encoding or angle encoding. These 4 numbers will be converted into angle. That is the reason why you will see a RY rotation. RY rotation will convert your classical data into angle put into the qubit. Does it answer your question?
Yeah. Yeah. One more thing that
Yeah.
I have done a course, not course. I have learned about this Qiskit thing. So already I was thinking of giving this examination, IBM one. But the circuits now, after listening to you, it looks like it doesn't mean much, right? Once it comes to machine learning, with respect to this circuit you made, there is much more to do, right?
There are a lot of things to do, but with an efforts by 1.5 months to 2 months efforts, you can appear for the Qiskit developer exam. Then pass it.
Okay, all right. Yeah.
Yeah.
Thank
But you need someone who knows in and out and then answer your questions properly. Otherwise, you will do trial and error or assumption. You will do a lot of things with assumption. So reduce the assumptions. That is very important.
All right.
Yeah.
Okay,
Many
thank you.
people when you start entering into the quantum career, they will have a lot of assumption. Okay, that's good question. Let us move on to the theory concept next. We will be there for only 5 minutes. After that, I want to show program because that will be more valuable than this theory part. Let me continue this one. Oh, sorry, this one. Sorry. So I just started this quantum encoding, right? This quantum encoding, but there are challenges for quantum machine learning. It is not always easy because there are 1 minute. Sir, I am in a session, sir. Shall I call you after, please? Okay, sir. Thank you, sir. Thank you, sir. Sorry. So the challenges of quantum machine learning is that we are in still the early stage because If you go for IBM system, you have access to only 127 qubits under your free account, open account. If you go for premium account, we cannot afford. And for other simulators, you can code up to 50, or if your laptop was 32 GB, you can code up to 27 or 30 qubits only. So it is very early stage, very complex, not only design and implement to understand, and it is evolving, and then we need to learn. So how to start? You have to start with the basics. Then there are a lot of online resources. Then obviously you have to follow the latest development. You know, the latest development, when we see the latest development, I would like to ask one question in the chat window. Please answer the question. It is very must. Have you heard about quantum reservoir computing? Please answer this question. Quick, very fast. I know 90% will say no. That is what latest. That's what I'm telling. Follow the latest development. Okay. I'm not going to explain what is quantum reservoir computing. For your information, I am working on quantum reservoir computing. So that is what the industry, and then that is what the latest development. So now you understood, right? What is that latest development? Please Google for quantum reservoir computing. You will understand. It is a time series forecasting. Okay, right. So now that is how you will be on the thing. Oh my God, this parameters quantum circuit comes and again. Now quantum variations classification. That is what the first entry point for QML, quantum machine learning. First entry point is variational classification. So the word variational means there are two parts, quantum part and classical part. Quantum part will perform the classification. Classical part will optimize the classification. So if you are coming from classical world, you know very well, your model will classify or regression. It will perform the regression operation or classical operation, and there will be an optimizer which will check the value, and then based on the value, it will check what should be the output value or whether it is converging. Then it will change the parameter, then feedback. So the fast forward or backward propagation, using these methods, we will improve the accuracy of each iteration in the classical world. Something similar to this one, quantum system also must have a variational approach, a quantum circuit for performing the calculation, a classical for optimizing this one. For this one, the variational part is built using the parameterized quantum circuit. That is where this parameterized comes again and again. So a parameter circuit will have a quantum part inside this one. The output will fed into classical. Then the classical part will change the parameter, then again feedback to the quantum circuit. Then that will run again. A quantum circuit is something like this, where here I can pass the parameters. Here, if I put as a def function, an argument to the def, something like that. That is what happening here. Make sense? That's what parameterized quantum circuit. Then variational quantum circuit, VQC. These two things are used to build this quantum variational classification. So I would like to write it here. So VQC as VQC is used to build quantum variational classification. Am I making sense? Parameterized quantum circuit as a variational quantum circuit used to build quantum variational classification. Beyond this, if we keep on telling this one, you don't understand anything. So I would like to take a pause here and show you one program, run the program, show the result, explain the concept, then come back to the theory. Is it good with everyone? We have another 1 hour. I believe that we need to have some break in between, because 2.5 hours, I can't expect people to stay. So have some water break, go for have some get some water, then come back. We will start in 2 minutes, exactly 2 minutes, no more than that. Don't waste time. We have to see lot of concepts. Please come back in 2 minutes. I'm stopping my. Yeah, I'm back. Now I have to share my whole screen. I'm sharing my entire screen because I'm going to switch between my application, program, all those things. Okay. This is going to be very fast forward. Don't worry. I will answer your question. Okay. I'm using a Linux system as my personal laptop, and all my development are in the. Okay, we have to start another. I can do this one. Right. So I have an environment. Um, so this is for IBM Qiskit 1.0.2. So I have activated this environment, and I would like to go for CD 2403 03. Yeah, no, not 03. If I go to okay, yeah. So here I have few programs. So let me run my Jupyter lab. I'm starting my Jupyter lab here. Yeah, hope you are seeing my Jupyter lab now. So here I have already built some programs for this demonstration purpose. First one is, let us start with the quantum support vector machine. This quantum support vector machine uses iris dataset. This iris dataset is, this one is the iris dataset. It has sepal length, sepal width, petal width, and then species, Setosa, versicolor, or virginica. Those who are not, anyone don't know what is iris dataset, please type here. I'm looking for no answer. If there is no, I okay. I'm assuming all of you know what is. Yeah, that's great. All of you know iris dataset, so my work is very easy. So I'm using this iris dataset, and these are all. If you are from Python background, you can understand these are all importing. And I moved this. Okay, let me first let me clear all outputs. Now let me run one by one. So these are all, when you are, I will share this program later. Devansh or Neevu will share with you. Then you are importing this one. After that, I am taking this data, then print. So data is loaded, and I'm creating data for sepal length, sepal, all those things, and then species is the output target. Why is this empty? Then it is the, I'm splitting training set and then testing set, and then this is the classical support machine model. Okay, so in the classical support vector, it is working, and then when I gave the input as 4 comma 4.4 comma 4.4 4.4, the classical system predicts this as iris virginica. So this is my predicted value, right? This is the classical, right? Oh, actually, this is I during the demo I used. Now enter the quantum world. In the quantum world, we are having quantum circuit library, primitive sampler. This one is version 1.02 compatible. So what I'm doing, I'm creating, so let us start from this one, the QSVC. QSVC need quantum kernel, ADA kernel. So it needs only one parameter. What is ADA kernel? What is ADA kernel? ADA kernel is the fidelity quantum kernel built using this fidelity and this feature map. Here the fidelity is created using compute and compute, and feature map is created using ZZ feature map. You got the point? There are kernel, that kernel is built using fidelity and feature map. Feature maps built using a function called ZZ feature map. Now these are the packages relevant for doing all these operations from IBM Qiskit. And using this one, I created the ADA kernel. And if you don't know what is that feature map, see here, the ADA feature map is the important thing. Why I am telling important thing? That is used to build this QSVM model. And there are a lot of things in that one. Then I'm building here, as usual, you can see here, a model is built using QSVC. Then it fit with training set, X training and then Y training. Then we are predicting with the test, X test. Then that X test is checked with the confusion matrix and the classification report. Now you can see here, oh my God, it is not very difficult. It looks like same classical model. Then why people are telling that quantum is very difficult, right? When you see this code, you will see that, oh my God, it is very simple. We have to import these packages and pass these values, and voila, we get the result, right? Indeed, it is so easy now. 2023, it is very easy. When I did quantum support vector machine in 2016 and 2017, yeah, 2007, 2016 and 2017, I struggled 3 months to figure it out how to feed the input. That time there is no Qiskit machine learning package. It was not there at that time. Everything I have to build from scratch. That time it was very difficult. But now, fortunately, you are equipped with Qiskit machine learning package from IBM Qiskit that abstracted most of the functionalities. So you are just simply creating an object using QSVC class and fit it, predict it. Then you get the result. See, it is very simple. You can see here, but quantum is wrongly predicting this as a versicolor, whereas classical is predicting as the, let me check, Virginica. So now you will wonder what is the accuracy. You see confusion matrix 15, 17, 7, 13, which means classical system has the high, you see the precision, accuracy 100%. Whereas if you see the quantum, you see the confusion matrix itself confusion, right? It is only 78% accuracy. But when I ran this for the one more demonstration for the college, it gave me 70, 80, 80 or 86% accuracy it gave me. When I ran first time, the same iris problem, when I ran in 2017, it gave me 67% accuracy. Now it is improving because on moreover, this is simulator. If I run it on a real quantum computer, it may give some more higher accuracy. Okay, so this is a quantum support vector machine, and it will make you to realize that quantum computing programming is not very difficult. It is very simple. Only thing should what package and then what approach you have to use. A support vector machine, you need a kernel. The kernel should be created using Fidelity quantum kernel. For that one, the fidelity should be, see, the compute and compute sampler, all those things. If you want to learn, my best suggestion is that go to Qiskit documentation. So this is the sampler, right? This is the sampler, Qiskit primitive sampler. So copy this, go to a new thing, Qiskit documentation. This is the right way to learn this thing. I think most of you follow this approach only, but few members on the, if they are hurry, they never worry about this one. No, I don't want to understand. That is not the right way. You have to understand what is this primitive, what is this sampler, because Qiskit version 1.02 drastically changed. It is a paradigm shift. If you are coming from older version, everything is changed now. So you have to learn these things without fail. So Qiskit sampler is, it runs, it is the execution where it is executing the circuit. There is one more approach. Apart from sampler, you can execute directly. That is a different approach, which is called, there is estimator. You use estimator also to run. You can use sampler also to run. Which one to choose? That is what you will learn over a period of time. Depending on your circuit, depending on the packages, whatever you are using, either you will choose estimator or sampler. For quantum support vector machine, we are using sampler. And fidelities are, let us see what is, but fidelity is coming from Qiskit algorithm. It is not Qiskit primitive. So if you search that one, again, that is another point. State fidelity, yeah, that one is, we have to go to GitHub packages, because this documentation may be old one. See, the state facility, what we are seeing now, you are viewing the API reference for an older version of Qiskit SDK, right? In Qiskit, in the older version, what is this version? Let me show here. It is version 0.96. In Qiskit 0.96, state fidelity was there under Qiskit quantum info, right? But in the latest version, it is not at all there. Then where is it? It is there in the different package called quantum algorithms. Sorry, Qiskit algorithms. This is a different package. So this is what you have to learn, because Qiskit algorithm is old version. Qiskit underscore algorithm is the latest version. You see here, it is a different package, like Qiskit underscore machine learning. Qiskit underscore algorithm is a new package. It is not Qiskit. It is like, you know, there is recently I watch YouTube WhatsApp video. One girl is wearing a red color shirt. His friend is telling, you are wearing red. No, it is not red. Then you are in red only. Yes, it is red, but it's not red. Then what? It is burgundy red. If you say that will be something like that. It is Qiskit, but not Qiskit. It is Qiskit algorithms. Qiskit underscore algorithms, right? Like this, it is Qiskit underscore machine learning. Then Qiskit. There are three packages. Qiskit 1.0, Qiskit underscore algorithm 0.3, Qiskit underscore machine learning, machine underscore learning 0.7. So whenever you are learning something, you have to hit the correct package or correct version. Then only you can understand what that code is doing. That is where most of the newbies will struggle. They will search that program, maybe the older version. When they try to run, it won't run properly in their Qiskit 1.02. They will get frustrated, because IBM Qiskit is frequently changing. You can see here from this one, the version, see this Qiskit SDK 1.02, right? If you see here 1.02, 4.6, this much of versions are there. And then people who started early with 0.9 and all, they have their working code which is in the 0.919, and that code has changed now. That time there is no quantum machine learning. Everything should be done with the 0.19. Am I making sense? Okay, now I am ready to answer your question for the 2 minutes. Then we will move on to quantum neural network. I will remove this output such that it will be easier for you to ask questions. Okay, now I removed all output. This is the quantum program. The last 4 things are quantum programs. The last 2. I will keep here for your question. Two more minutes. Yes, I strongly believe that answering your question, move up, that will help a lot.
Yes, sir, I have a question.
Yeah, please go ahead.
As you said, the accuracy level of this was around 76 or 77, if I'm not wrong. So is there anything that I could fine tune it or doing something so that the accuracy gets improved? Or does it remain the same?
There is one way to improve the accuracy. One is running this, trying this on the see, now I'm running on the simulator, my local system, right? And that is one reason. You can try to run on if you run this on Google Colab, you will get different result. And if you running on some powerful system, 64 GB or a GPU enabled system, you can get a better result. Or else if you have budget, you can run on real quantum computers. That time you can get more increased accuracy. This is the step by step way to increase the accuracy, or how to say, experiment with various targets, CPUs, sorry, simulators or QPUs.
Yes, sir. Thank
Does
you,
it
sir.
answer?
As of now, what you have shown is actually classical data with quantum algorithms. This has
Correct.
not been converted to a quantum, as you said, the basis encoding, which is amplitude encoding or phase encoding. That has not been converted in this, right?
No, this is amplitude encoding. This is the feature map. Yeah, that
Okay.
is amplitude encoding. Sorry, angle
Okay.
encoding. Sorry, phase encoding.
Okay. If I want to convert it into the one more encoding thing, anything that I have to do it in this ZZ feature map.
You cannot arbitrarily encode. See, the encoding is not for accuracy. Encoding is based on the algorithm. For your algorithm, it can handle amplitude only. For example, if you are going to grow your search, there you cannot use phase encoding. You have to use amplitude encoding only. It depends on the algorithm. The phase encoding, if you think that I can use amplitude encoding, then iris problem, try to, it won't work, because iris or the support vector machine is manipulating the angle of your of your qubit system to find out the class. Am I making sense? See, imagine this way: you are a baseball player or cricket batsman sitting or standing in the center of a globe, and when many bowlers are throwing ball towards you at the same time, you are hitting all balls, and the balls are hitting the sphere. Imagine that way. Now you are measuring the angle of the balls to identify which balls falls under which area. That area is one class. So here, that angle is the only way to classify the data. Here you cannot use amplitude. Am I making sense?
Yes, sir. Yes.
Yeah. So it is not, you cannot think this way. I can change amplitude encoding, increase the accuracy for support vector machine. No, that won't work, because support vector machine always angle. Whether it is a Qiskit or penny lane, it is always angle only. I can show you a penny lane example also. There also they are using a classical angle. They will use numpy linear operation to rotate by cos pi theta plus sin pi by 2, something like that they will do, and then rotate the angle. After that, they will feed to support vector machine in the penny lane model. Okay. Hope that answered your question. Any other question? If you explore the ZZ feature map, you can understand more about this algorithm. Let me give what is ZZ feature map. So ZZ feature map is second order poly Z evaluation circuit. Here you can see here it is a U12 theta. So it is an angle rotation. I would like to show one image here. Here you see this one. This is how your angle phase encoding is working. So this is the way how your value are mapped. Considering this one, we have to use angle encoding only. So you can imagine that your qubit values are on the perimeter of the Bloch sphere. So certain area, if it is cut beyond that, that is one class, and then if it goes this way, it is another class. Like that, you will classify. You see here, this area is one class, and this area is another class. This area is another class. Like that, you will classify. That is how this system is working. You see here, Z feature map. There are multiple ways also to do that one. Okay, any other question? If not, we can move on to the next one. Classical computers cannot work well on float data types. We face numerical instability. How quantum computer can handle all probabilities float values? Okay, Arvind asked one question. Classical computer cannot work well on float data types. We face numerical instability. How quantum computers can handle all probabilistic float values? Yeah. See, the nature of quantum is not real numbers. It is the complex number, which means the complex number is used to represent the qubit state. The qubit state is the complex number. So any real number can be represented as a complex number. So that question what you are asking is handled effectively by the complex numbers in the Hilbert space, because that's the inner product of these two things. Otherwise, your output will go outside of the Bloch sphere or inside the Bloch sphere. But actually, we need everything exactly on the perimeter. Does it make sense? Arvind, does it answer your question? Cool. Right. Let us move on to next problem, which is the quantum neural network. This is very interesting. Here I am using Penny Lane. If you are into quantum machine learning, you cannot skip Penny Lane. Penny Lane is the our favorite package for implementing quantum machine learning. So this is the Penny Lane URL. It is Nadu Penny Lane. So here they have a lot of examples. I recommend. Oh my God, this one. Sorry.
Karthiganesh, sorry for disturbance. Will you please zoom in to some extent while you are showing these windows? Very small.
What about now? Is it
Will
okay?
you please zoom in the windows, please? The coding window.
Yeah.
While you demonstrate the coding windows, please zoom in to some extent.
Coding window. Okay. Okay. Is that okay?
Thank you. Good.
Okay. Right. Cool. Cool. Thanks for that one. Okay. Right. So here it is Penny Lane. Here, if you go to demos, you can see there are a lot of demos built in Penny Lane, and quantum machine learning. They have 34 examples. Oh my! Last month I saw only 32. Now they have added 2 more. Just very interesting programs are there. If you able to experiment or run all these programs and understand all those programs, your confidence on the quantum machine learning will be shoot up. So I recommend try to practice all these Penny Lane programs. Right? Please contact Nivu or Devans if you need more help on this one. We have training programs for all those things. Through Nunari Academy, we can deliver you training, all those things. Okay. So these are all very useful thing. You try to understand, you see QA to LSTM, there are different level of thing. R measure, my God. Then torch layer, all those things. Okay, right. Now let me come back to the program. So now you learned, right? Qiskit is one part of game. If you are into quantum machine learning, PennyLane is your main tool. So start learning PennyLane also. So here it is the way to PennyLane is imported, and from PennyLane I am importing QAVA. In this program I am using TensorFlow also. Then this is the graph, mathematical graph, not chart or not this one. This is the mathematical graph, which is like this kind of structure. So I stopped all those things. I cleared all the output. I will run and then show you. Okay, let me run again. I will explain. So this is the graph what I'm telling. So max cut, we have to find out the max cut, because max cut is one of the optimization problem. This is the combination of optimization and quantum neural network. You will see here I'm importing the QAOA, then QML. So here this is the random chart or random network what I have. In this network I am trying to find out this is another network. Here I am applying a long short-term memory model. It's a classical model. See, this LSTM is the classical model. This layer is fed into a quantum approximation optimization algorithm, QAOA algorithm. So the QAOA will perform max cut. If you are trying to do max cut using classical, that will go recursive model. It will take a lot of time, because that is the NP hard problem. Even the traveling salesman problem, that also falls under this category. These things will grow exponentially if we add one more node. Just add one more node, it will grow exponentially. That's why we are using a max cut problem or max cut algorithm provided by quantum computing, which is called QAOA. So here I am creating the graph list, and this one is the Z1, Z0, Z1, Z0. That concept is the uh, that one is the graph. I will explain what is that layer, that one, that each operation, 0 bit, that operation, Z operation, like that. We call it as a label op, that will come. I forgot the exact term. Then comes a recurring neural network, RNN iteration. This recurring neural network here, again, if you see here, these are all classical part till here. See, cell, all these things are recurrent neural RNN part, or the training step also. The quantum part will come in this area. See the new cost QAOA. Whenever you are calling QAOA from graph, that is the quantum part. Remaining part are classical part. So what is the QAOA? That's what we have to understand. Here is the QAOA. In the QAOA, if you see the algorithm, there are wire means number of qubit. The number of qubit is the length of graph node. How many nodes? That number of qubits. Then cost and mixer is the QAOA max cut. So this quantum algorithm max cut for the given graph, that will spit out cost and mixer. And these two things are, you see here, the QAOA max cut. Let me check. QAOA max cut. It is actually, it is the package we have to see. It is the only place, which means you have to copy this and then learn from PennyLane documentation how this is working. Okay, yeah, this is the correct one, because that's what the PennyLane documentation we have to learn. documentation, API. Go to API. That is the correct place. You can learn penny lane, these things. If you normally search, it will confuse you, or it will go somewhere else. You will get lost. So QML, this is QML QAOA. In this one, you have max cut, right? This is the max cut. So what is the max cut is doing? Returns a QAOA cost Hamiltonian and recommend mixer corresponding. Mixer corresponding to the max cut for a given graph. So what is the problem? Here is the mathematical problem. If it is a Hamiltonian of cost 1 over 2 sigma ij to each edge of each graph, it is zi zj. So the z is the poly z operation. Again, z feature map what we saw in the Qiskit, something similar to this one. Here also it is the poly z operation. That is why here you saw these labels. These labels, z like this. This is the operation, that rotation. That is why this operation zi by zi minus I is the identity. You see here, identity in quantum, not only in quantum, even classical also, it won't do anything, right? So it will keep the value as it is. So the mixer Hamiltonian recorded from max set is a H mixer or X mixer applied to all wires. Here you will see sample program. So coming back to the code, this portion, what we are seeing now, this is the actual. Oh my God, where I lost it. Okay, right here it is. So this QAOA returns cost and mixer. Then there is a two layers, QAOA layer with the two parameters gamma and alpha. It is again calling QAOA cost layer, QAOA mix layer, and then this QAOA layer is called in the circuit. This circuit is called in the Hamiltonian. You can see here the Hamiltonian calls QML Q node. This is the circuit. This is the quantum circuit, and then differential is the back propagation, and then interface the tensor flow interface. That cost is returned. So finally, the Hamiltonian is returned. So the cost of the parameters is returned. So this is the quantum portion for this neural network. See, this neural network is mix of QAA1, QNN. Why I selected this one? With one program, I will be able to demonstrate both the QAOA as well as QNN. That's the reason why I selected this one. There are simple straightforward QNN problems also. You can experiment that also. That's why the Pennyline has good combination. Qiskit also has Qiskit neural networks have two more models, or actually three more models. You can experiment that one also. Let me go back to other program. Okay, I would wait for one more minutes for answer one question. Anyone have one question? One question I ready to answer related to this one. Any question? Okay, no more questions. That's cool. Then move on to another model. This is very interesting. I would like to go for QCN, quantum convolutional neural network. This is very powerful concept because this one is image classification. So I will run this program, and all this program will work in my system. I restart the kernel. Okay, let me run this one. This one is also Pennyline, and it is running on. It uses both OpenCV and TensorFlow. You can see it is heavyweight, right? All the packages are heavy packages. So as I earlier told you, you can run it on your laptop. If you have a laptop 32 GB, minimum 32 GB is recommended. Otherwise, all these programs will take a lot of time, and then your laptop may hang. So I recommend run all those things in your, if you have 32 GB system, If your laptop is not 32 GB, run it on any one of the EC2 or Azure or any other cloud system. So here I have 5 epochs and building the training and test set. Okay. Oh, this one is earlier I had some problem. That's why I printed. I can remove this one. Then normalization. See, this model is very another example. I will explain this one. Then quantum pre-process. So it will run for some more time. While it is running, I will explain the code. Okay, here also there are two approaches, classical as well as quantum, right? If you see this code, see this one is my model, right? In the my model, I defined my model. This is the quantum model, also my model. Classical model is also my model. The only difference is that the input is the quantum data. Here, input is the classical data. That is the only difference. Other than that, see, that is the reason why I selected this QCNN. When you are applying QCNN, the model remains classical only. There is no change. We are not having a separate model for quantum, but the input is converted. Here, the Q test image, if you check what is the Q test image, it is the 9th place, we know first place. In the first place, what I am doing here, see, this code you understood, right? Here, what I am taking from my QCNN train. So this is my QCNN folder. Here I have test and then training folder. Here I have images, right? Like this, I have a lot of images. So in this program, what I'm doing in the classical world, I'm going to the folder, taking all the data and then storing them into the training image. See, training image, training label. Like this, I'm having testing image, testing label. So just I'm doing opening the classical folder, reading the images, putting them into an array. After that, what I'm doing, after taking the data, that image data I'm converting into a numpy array as a number. After that numpy array generated, that is what the trick here, what I'm doing here, I'm creating a convolution image. See, the image is converted into a quantum data using this package. Here, what I'm doing, this function, what I'm doing here, you see this conv function. I'm calling that conv function here. You see here, Q train images. I'm appending with the quan of image. The image is the train image. You can see here for ID is equal to img enumerate train image. I'm using the train image to create a quantum image. That created quantum image is stored into the Q train images. That is the only part. This input is given to a classical model. My model is that a standard Keras model with the 2 layers, flatten and then dense. This is the classical one is for convolution, other one is the pooling. Those 2 layers are created and it is using the gradient descent mod called Adam optimizer. That's it. A standard classical model is built. A classical machine learning model with the quantum data, I am able to build a quantum convolution neural network. This is one approach. So there are 3 approaches we have seen. In the quantum support vector machine, it is an iris data where I used angle encoding. In next problem, QNN, I used a network data which is passed to a QAOA quantum approximation optimization algorithm. and then cost mixer Hamiltonian is generated. That is fed into a neural network, and back propagation method is used. In the third approach, I encoded my image into a quantum data and fed that quantum data to a classical convolution layer, such that I'm able to build a quantum convolutional neural network. So these are the three approaches. I would like to stop here because we have only 40 minutes left. I would like to answer your questions. I'm expecting a lot of questions, so I'm stopping here. Feel free to go back to any concepts, whatever you have discussed for the past 2 hours. I will explain those concepts, because success of these kind of programs lies in lot of question and answer. That's why I'm allocating another 15 minutes for the next 13 minutes for Q&A. Any question, if you are not able to ask, please type in the chat window. I am ready to answer your questions. So we have demonstrated three things. I have one more thing called QGAN. That will be overkilling, but I will show while if you don't ask any question. This QGAN, it is a quantum generator classical discriminator. And whatever real vector we are giving, that will be the generated real vector will be checked with the see, real vector is a 0.26, but the generator output was 0.02. Not this one. Yeah, actually that is the scaling. So if you see here, 0.2, this one is 0.48, this one is 0.97. So it is more close to the real, but that algorithm has a discriminator, a classical discriminator, and then quantum generator. So here the quantum generator, you can see here QML node, real discriminator circuit, generator discriminator circuit. These two things are quantum node, and then there is a quantum rotation operation here for discriminator and the generator. Then again here also angle encoding or phase encoding. Okay, so we have 10 more minutes. Any question? If no more question, Devans, I would like to hand over the session to you.
Karthiganesh, I'm not having a question, but could you throw some light on that quantum reservoir computing?
Oh, okay. The quantum reservoir computing is for time series forecasting. If you want to perform time series forecasting, quantum reservoir computing is the new approach for the time series forecasting. So it is the way how it is working. You have to feed the time as the one of the data point, where the data related to that time will be put into one reservoir concept. Like water is coming onto a reservoir, right? When there is a rainfall, water is keep on coming to reservoir. So based on the incoming flow, we will be able to hold it or tell that how much value I can accumulate over a period of time. That kind of calculation, I cannot go beyond that one. It's still on the research stage, so I'm part of the research team. I cannot reveal all the concepts. But there are a lot of, if you go for Googling, you can find very less information. But that is a good point to know that what is happening in the latest development. I just asked to kindle your interest. There are a lot of things are going on in this industry, to show that only I called. Devansh or Nivu, anyone are here?
Yeah, sir.
Yeah, I think if no more questions, I would like to hand over to you. Then, if you have any final sessions about your Nunari Academy, please share with the audience what are you doing and what are the things, how they can contact you, all those things, please.
Sure, sir. Sure, sir. First of all, thank you for your time. It was like an enlightenment event, like kind of a thing. I think audience can substantially benefit from your thoughts and words. Uh, about Nunneri or about contacting us, I think most of you would have received a mail with the registration link, or if you haven't received, you can just head to aitamilnadu.org. You will find all the details there. It's a non-profit organization or a community basically. So we have experts from different industries. We have supporters, volunteers from different parts of Tamil Nadu, and we have members over 1,000+ members who join us in this knowledge sharing path and stuff. Uh, for Nunnery, we have academic solutions and like labs, that is research R&D and stuff. So not talking much about Nunnery. But if you want to connect with us, you can always head to LinkedIn, or we have our own website. You can head there. You can contact me. I believe everyone who have registered here would have received my phone number or my contact number with included to the mail, or you can just head to nunnailabs.com, and in the contact section you can find my phone number. So nothing like you can find it anywhere. So if you guys have any doubt, or if you guys want a more session based on quantum machine learning, you want more like a panel of quantum ML experts, we will be happy to arrange that. If you want offline events, we'll be happy to arrange that. So we are basically, as a community, we are trying to share the knowledge or bring the experts to the new young generation, or even the professionals, like the expert seasoned professionals. So that's our basic mission and vision. I think that's in the workshop here. It's been great for 2.5 hours. We even had a break of a 2-3 minute, and it's yeah, it's great. People have so much doubts. I think still people have doubt, and since we are running out of time, we are closing this. It was too great. Thank you all for joining us, and hope to see you in any further offline sessions and stuff. And also, we are planning an offline event by 11th May. It's on Gemini and stuff like that. So you will receive updates via mail and also on the LinkedIn page. So do follow that. And that's it. I will end the workshop here. Thank you all. Thank you for joining us. Thank you, sir. It's again a great
Thanks,
thanks
Devansh.
to.
It's my pleasure. If anyone asks my contact, feel free to share with them. I'm happy to
Sure, sir.
support. Thank
Sure,
you.
sure, sir. Thank you, sir.
Thanks, Karthi. Very good presentation. Thank you.
Bye bye.